PARP inhibitor treatment has been around for a while, and people are increasingly looking at PARP inhibitor resistance. The question is, how come? How come these people are developing this resistance?
Hello and welcome to Strand Explains, a podcast where we discuss what's happening in the world of precision medicine, from weird case studies and interesting facts to interviews with leaders in the industry. Hi, RK. What exactly are we talking about today? Today morning you texted me saying, hey, let's record a podcast. I have something interesting to talk about, and left it there with a mystery. So, what are we talking about today?
Oh yeah, I thought we'll talk about PARP inhibitor treatment and resistance, especially in ovarian and breast cancers.
That sounds pretty cool. So, what is that? I know very, I mean, I know what breast cancers are to some extent, but yeah, could you give us some context?
Yeah, and our focus has always been oncology, and breast and ovarian cancers are very high incidence in India. And we recently released our homologous recombination deficiency (HRD) panel, right? And so one of the pieces of context here is that release of that HRD panel is kind of tied to a lot of the stuff that we are planning to do over the next several years in breast and ovarian cancers, especially. So I thought, what better time than now to talk about this?
Yeah, that sounds great. So you mentioned that there's an HRD assay, and my understanding is HRD has to do with homologous recombination repair or HRR. But what exactly is the connection between that? I know that both of these have to do with the repair mechanisms that exist in cells for
Yeah.
DNA repair. But if you could elucidate that a little bit, that would be great.
Yes. So DNA repair, there's many known mechanisms of DNA repair. Two dominant ones are homologous recombination repair and non-homologous end joining. Uh, so these are both sort of ways in which when cells have DNA damage of any kind, right? And DNA damage occurs as a matter of course, especially when, for instance, cell division is occurring. That damage is actually repaired by an entire pathway that suddenly gets activated whenever it senses that this DNA is about to go to seed and we need to rescue the cell because it can't really go in there with damaged DNA, right? So so those two mechanisms of repair exist, and the more accurate of these two is homologous recombination, and it just in the vast majority of individuals, homologous recombination ensures that in the presence of DNA damage, there is repair occurring subsequent to that, and that repair restores the DNA to what it was meant to be.
I see. So you mentioned homologous repair, and if I'm not mistaken, that's the same technology they use in CRISPR, where they exploit this DNA repair mechanism pathway to create those edits by not without going into it far too much. Sorry, they introduce a template strand so that when that homologous repair happens, you use the guide RNA as a template rather than the complementary DNA strand. And it's so fascinating that this very basic process that exists at a cellular level of, hey, there's been a break in the DNA, or there's something wrong in the DNA, we need to repair it. You can exploit it and use it in so many different ways, where in the context of CRISPR you're exploiting it, but in the context of PARP inhibitors, like you mentioned, you're targeting it.
Yes, you are targeting HRR in a way with PARP inhibitor treatment, but as far as the assay goes, it's very simple. All it tells you, and this is the assay that we released a few months ago, it it's an NGS based assay which tells you if there are mutations in you know the genes known to be part of the HRR pathway. So in other words, it tells you if homologous recombination uh, is impaired, right? And so that entire pathway, if it is impaired, then that entire pathway is not available for DNA repair. So the cell has to repair itself with the NHEJ pathway or other more error prone pathways, and that's sort of the information that the HRR pathway gives you.
That's pretty cool. I think I didn't I was also a little confused, but thanks for clarifying and very fascinating. Getting back to kind of maybe where we started this podcast on and what you would said you want to talk about, how does HRR and HRD come into play with PARP inhibitors? Why are we? What is the context here, and why are they important when it comes to PARP inhibitors?
Yeah, so when people have a homologous recombination deficiency, that means that pathway is inhibited, uh, their cancer cannot repair uh, breaks in DNA as easily as maybe in other situations, right? And so the underlying thesis of PARP inhibitor treatment is that PARP, first of all, is sort of precedes the repair pathways, not just the HR pathway, but all many other repair pathways as well. And the cancer already cannot repair itself via HRR because it's HR deficient. And if you inhibit PARP altogether, then the cancer has no means to repair itself, essentially. So you're inhibiting all means of DNA repair by the cancer and causing something called synthetic lethality, which is just a fancy name for saying you're killing the cancer synthetically by saying that some protein is inhibited that basically disables all of its repair mechanism.
I see. And so basically, you're able to kind of target the cancers because you already have one repair mechanism not working, which is that HRR pathway. And so this way, you're able to knock out both pathways and potentially lead to a point where, from what I understand, you're saying that cancer just doesn't have a way of fixing itself when there is DNA breaks or errors in the DNA.
Yeah. So the PARP inhibitor treatment has been around for a while, right? Um, the one that a lot of people might know about is olaparib. I think it was the first PARP inhibitor on the market, but there are a few others now. They all work on the same general principle that one has to inhibit PARP, and then repair mechanisms are inhibited. Cancer cells can't repair themselves, and then they die. And it's interesting, and this comes to the second reason we're here today, which is that people are increasingly looking at PARP inhibitor resistance, right? And they have been also for a while, but I think the interest is growing. PARP inhibitors are very successful treatments. Olaparib, for example, people on olaparib are on it for many years, and they're essentially, they have very few symptoms, and it looks like their cancer is fine. But a lot of them, the cancer does come back, right? So they develop resistance to PARP inhibitor treatment, right? So the question that people are asking is, how come? How come these people are um, developing this resistance? And there's many hypotheses, but the one that's simplest is the one that we can just talk very briefly about, is that
Sure.
it's just that this HR pathway that was deficient earlier, all of those cells that are deficient are dead. But the ones that survive and evolve and persist are the ones that can repair themselves. So it's as simple as all of these other mechanisms of resistance that we've been looking at. Like last year we wrote a number of posts on it. Exactly, and this is also a targeted therapy, right? And what ends up happening is when you're targeting a certain pathway, any set of cells that have to go through that pathway will die. But all this means is that the ones that don't, right, they persist, and then they are going to survive, and then they will continue, right?
Resistant just by the nature of being, not by anything else.
Right. And eventually they become the dominant form of cancer cell, right? And it's funny, we've been looking at evolution. Well, I mean, obviously Omicron has come out, the COVID variant, and so COVID and other infectious diseases, they evolve too. um, But I think infectious diseases by their very nature can spread from person to person, so their evolution takes them on a different track, right? I mean, if there's a colony of infectious disease organisms, then they can just keep jumping, right? They're not stuck to any given host, right? But cancer is, right? Cancer has to live, coexist with the host. There is no other place for it to go, right?
Hmm.
And so in that sense, its evolution does not take it through a path where it can coexist with the host,
It's
whereas
constrained.
it's just constrained, it can't go anywhere else, right? Whereas for COVID and other infectious diseases, their evolution can and sometimes often does to take them through a more infectious path, which makes which ensures that they keep moving from host to host, but also maybe not as deleterious to the host.
Definitely. You and I had a conversation, I think, a few podcast episodes ago about how, with the advent of Omicron, we are seeing that it's becoming more endemic. So, and typically with the evolution of a lot of infectious viruses and other pathogens,
Yeah.
what ends up happening in, like, if you look at the common cold as the best example, it becomes a nuisance more than anything,
Right.
where its lethality reduces, but its transmissibility increases. And that's what we think we're seeing with Omicron.
Right.
However, in the context of a cancer, for that to occur, you need to have, like you were mentioning, that ability to move from host to host and ability to evolve outside of a single context or a single environment. And in the form of, in when it comes to cancers, because they come from within, for lack of a better word,
Yeah.
the cells come from the host themselves, and
Yeah.
they are host cells that have been evolved, that it just doesn't work the same way. And so that's
Yeah.
why looking at the evolution of cancer cells is very different from looking at the evolution of pathogens or anything else. And I think that's why it's such a fascinating avenue, and it's really exciting to think about. Well, maybe exciting is the wrong word, but there's a lot to learn in that space, because the way they evolve against, for instance, PARP inhibitors or any other targeted therapies is so different. It was really cool to really just listen and learn about something that I knew virtually nothing about today morning, and hopefully I know a little more about. We typically have a more scripted podcast with, if nothing else, just some questions that we can ask each other and some basic research. And it was really fun to get to just sit here and hear you talk and explain how these things, which again are such basic things when you think about it, but the big impacts they can have on our health and the way we treat cancers and other health related issues.
Yep. My pleasure. Thank you.